Good evening, everyone, and welcome to the McMaster University LIVELab. I'd like to begin by acknowledging that the land on which we are currently gathered sits on the traditional territories of the Mississauga and Haudenosaunee nations, and within the lands protected by the Dish with One Spoon Wampum Agreement. And as an academic institution, it's important to note that teachings from the First Peoples of Canada have had an enormous impact on all areas of academic pursuits, from science to engineering to humanities. And without Indigenous knowledge, much of the current research that you'll hear about tonight would not be possible. My name is Joe Kim, and I'm the academic director of the McCall MacBain Postdoctoral Fellows Teaching and Leadership Program. And together with Katie George, we run this program dedicated to creating professional development opportunities for postdoctoral scholars from McMaster University, locally, and across Canada. And one of our fundamental goals is to provide early career researchers with tools to improve their knowledge translation skills and to be able to convey their research impact, which is exactly what we'll be doing tonight. But before we get started, I want you to take a look around you. We've gathered tonight in one of the most unique research centers and performance spaces in Canada. The large interactive virtual environment lab, or as we call it, the LIVELab, is a unique 106-seat research performance hall designed to investigate the experience of music, dance, multimedia presentations, and human interaction. The space includes acoustic control, sound recording, but also we can measure from the audience behavioral responses, movements like motion capture, brain responses through EEG, muscle tension through EMG, heart rate, breathing rate, and even sweating responses. So, for example, as a researcher, a study I've done in this lab, I'm interested in understanding what are the conditions that lead students to pay attention during a lecture. One way I could do this study is just in an isolated lab, nothing to do with a real lecture hall like this. But in a room, in a facility like this, we can actually have a real lecture going on. And from the audience, from students sitting in the audience, I could be measuring EEG, galvanic skin response, and heart rate variability as a neurophysiological measure of how well they're actually paying attention, instead of just asking, are you paying attention during this lecture? I know that you're going to enjoy this evening's talks from the fields of psychology, engineering, healthcare, humanities, and science. We are very excited to bring you to the next generation of thought leaders that will help to move our world forward. I'd now like to pass things over to Katie George to introduce this evening's judges.
Thank you, Joe. My name is Katie George, and I know many of the folks in the room, but for those who don't know me, I am the program manager for the McCall MacBain Postdoctoral Fellows Teaching and Leadership Program. I have the privilege of working with incredible researchers every single day. Postdoctoral scholars create transformative research that tackles real-world problems. Their work can change our lives and the world around us. I'm excited to welcome 10 postdocs this evening to share some of their research with you and give you just even a small little glimpse through the window of the incredible people that work in our academic institutions, government facilities, and healthcare settings. Although much of tonight's research takes place in the walls of the academy, our goal is to show you how impactful this research can be on our communities, as well as each and every one of our lives. You will hear from, and I have to edit, we had one speaker unable to attend tonight, so it will be 9 elite researchers from institutions across Ontario. They represent the top 9 talks from the 5MRT, which is a preliminary round. They were tasked to translate their complex research, and you'll see as I introduce each speaker, some of the words I don't even know as words, and they might be complicated to you as well, so give me a little bit of grace. But their research is extremely intricate, and they were tasked to squash it into 5 minutes. And on top of that, we have a community audience of interdisciplinary folks. So they have to take all of what they know and explain it in a way that makes sense to everyone. That is no easy task, trust me. At the end of the evening, we will have a brief question and answer period, because if you're anything like me, you're going to have a million questions, and that's okay. We just ask that you hold them until the end of the evening during our Q&A period. You will also have an opportunity to vote for your favorite talk. The winner of the popular vote will be given the People's Choice Award. You can find the voting QR code on your programs. For our online audiences, we will put a QR code up for you so that you can vote at that particular time. Voting should not be open yet, so wait until you see the speakers to cast your votes. Now this year, to assist with judging this year's talks for the 2026 5MRT finals, we have 4 esteemed academics from around Ontario. Judges, as I call your name, please stand to be acknowledged. First, I would like to introduce last year's winner, Dr. Amit Shakiri. There he is. Dr. Shakiri comes from the University of Toronto and is a senior research scientist in Quattero and a postdoctoral fellow at the University of Toronto and Toronto General Hospital. His work focuses on biomaterials, 3D bioprinting, and organ-on-chip technologies. You heard that correctly, with applications in cancer research, disease modeling, and diagnostic platforms. He received his PhD in mechanical engineering from McMaster University in 2020, and he's the recipient of the NSERC Postdoctoral Fellowship. His research has resulted in multiple publications and patents. Our second judge, also hailing from the University of Toronto, is Dr. Afshin Abrashamkar. Dr. Abrashamkar is a research officer in the Medical Devices Research Centre at the National Research Council of Canada, or NRC, and an assistant professor in the Department of Mechanical and Industrial Engineering at the University of Toronto. Afshin holds a PhD in chemical engineering from UTH Zurich and completed postdoctoral fellowships at PSL, Université Paris, and McMaster University, where he also participated in the McCall MacBain Postdoctoral Fellows Teaching and Leadership Program. So it's nice to see you back, Afshin. His multidisciplinary research is at the intersection of microfluidics, biomedical engineering, and material science. He aims to develop new microfluidic platforms for controlled fabrication and processing of bio-inspired advanced materials for health-related and biomedical applications. Next, please welcome Dr. Thomas Kazmierczak. Dr. Kazmierczak is an award-winning biomedical researcher and scientific communicator, specializing in precision medicine, hematology, and AI-driven drug discovery. With a PhD in molecular biology and over 3 years of postdoctoral experience, his research integrates synthetic biology peptide therapeutics, which is a mouthful, and AI approaches to addressing unmet needs in rare bleeding disorders. His goal is to translate molecular insights into novel diagnostic and therapeutics. His contributions to both science and medicine have been recognized with prestigious scientific and community awards. And last, but certainly not least, I bring you Dr. Cindy Chan. Dr. Chan is a Senior Knowledge Mobilization Specialist from Research Impact Canada, or RIC. She leads network coordination efforts and supports the design and delivery of the network's national knowledge mobilization events and initiatives. With a strong focus on operations, Sandy works behind the scenes to strengthen connections across the network's ecosystem while supporting the advancement of impact-driven engagement across Canada. Thank you all for your dedication to early career research in Canada and knowledge mobilization. All right, I think you've heard enough from me, so let's get our speakers up here. The first speaker of the evening is Dr. Peter Adesina. And to get us started, he will join us from the University of Toronto. Dr. Adesina holds a PhD in geotechnical engineering from Imperial College of London. He has held research positions at the University of Bath, UK, INRAE in France, and the University of British Columbia, as well as the University of Toronto. His research integrates advanced laboratory and numerical methods, including high-performance computing to characterize soils and mitigate failure in civil infrastructure. Please welcome Dr. Peter Adesina.
Hello, everyone. I have a quick question for you. How many persons here, by show of hands, have used a phone, a computer, or any modern technology before? Okay, great. Pretty much everyone. Now, all of these modern technologies that we've all used at one point or the other in our lives are made from minerals that are mined from the ground. When we perform mining, we generate waste that we call tailings. Tailings we store in what we refer to as tailing dams. My name is Peter Adesina, and what I'd like to share with you today is my contribution to the delivery of resilient dams and communities by mitigating a failure mechanism which we call liquefaction in tailing dams. So in the last decade, we've had major tailing dams failures around the world, including here in Canada. In Canada, we had the incident in Alberta and the one in British Columbia, both of which had huge impact on the communities living downstream. Outside of Canada, we had the Brumadinho Dam disaster that occurred in Brazil, which killed over 250 people in one instance. So 2,650 people have been killed by tailing dams failures around the world. 317,000 more have been displaced. We have about 500 tailing dams in Canada, almost half of which we have here in Ontario. Canada's mining activities is going to increase. Why? Because we need lots and lots of rare earth minerals for defense equipment manufacturing and also for the development of modern technologies. And in fact, Canada is taking the lead in the defense defense equipment manufacturing to reduce our reliance on our southern neighbor. And so with more mining activities in Canada, that means that we would have more of these failures in the future. So tailing dams failures are caused by different mechanisms, chief of which is liquefaction. So what is liquefaction? Imagine that you have a stable soil and you subject it to shaking, let's say from an earthquake. If you shake the soil well enough, it's going to begin to flow like a liquid. This is what we call liquefaction. What happens in a liquefaction scenario is that the soil goes from a state where the particles have contact to one where contacts are lost. And this is because of increase in water pressure within the soil. So we can have earthquake-induced liquefaction, and in Canada we have about 4,000 earthquakes occurring per year, which means we have huge potential for earthquake-induced liquefaction in the country. Hopefully one doesn't happen as we are here. We also have another kind of liquefaction that we call static-induced liquefaction. This is caused by the self-weight of a dam. It is actually the one that killed over 250 people in one instance in Brazil. So the essence of my research is to prevent and mitigate liquefaction in dams. And I do this by assessing whether the soil in a dam is susceptible to liquefaction or not, using what we call the cone penetration test. So I have another quick question. How many persons here have taken an injection before? I mean, from a doctor. Okay, so cone penetration test, we can liken it to pushing an injection syringe within a soil. But this syringe, though, has sensors within it that can help us obtain parameters that can give us an indication of the state of the soil within a dam. So we can perform cone penetration test in situ, but it is expensive and difficult on the field. It is the reason why we perform cone penetration tests within a calibration chamber that we have within the lab, where we have control over influencing factors. So when you push a cone within a soil, you obtain the resistance of the soil against the push of the cone, and we call this the cone tip resistance. We then plot this tip resistance against a measure of the density of the soil. So if the soil is dense, we have high resistance, and if the soil is loose, we have low resistance. If the soil in a dam falls in the region that indicates that the soil is loose, we can conclude that this dam is susceptible to liquefaction. So with my research, we can assess liquefaction susceptibility in tailing dams to prevent failures. This enables us to protect communities living downstream of tailing dams, thereby preventing their untimely deaths. And this means you and I can use our phones, our computers, all of our modern technologies with less blood on our hands. Thank you.
Thank you so much, Dr. Adesina, for such a fascinating presentation. Our next speaker, there we go, there she is. Our next speaker is Dr. Megan McHugh. Dr. McHugh is a postdoctoral researcher at McMaster University, working with Dr. Thomas Hawk and Dr. Irina Rybaka. They are studying the impact of type 1 diabetes on skeletal muscle and exploring the potential benefits of exercise. Fun fact about Megan, and before I say this, I want to prime you all to not judge her because she is a brilliant researcher despite this fact. She attended the midnight screening for every single Twilight movie, including lining up for several hours. No judgment. And quite frankly, she says she'd do it again and again. So there you go. Please welcome Dr. Megan McHugh.
I would do it again. All right, so I wouldn't blame you if muscle wasn't the first thing that came to mind when you heard type 1 diabetes, but hopefully after the next 5 minutes, it might at least be the second, and you know what? I would settle for the third. So type 1 diabetes occurs when the body is no longer able to produce insulin on its own. Insulin is the molecule that tells our tissues to open up their doors and let glucose in. This contributes to blood glucose control and also ensures that tissues have the energy they need to function. So without insulin, we can't really manage our blood glucose. Luckily, if you have type 1 diabetes, it can be pretty well managed with lifelong insulin therapy. But this therapy is really complex because blood glucose can be a little bit unpredictable. It's going to be impacted by what you've eaten, how much sleep you've had, if you're stressed, and something as seemingly unrelated as a sunburn can actually impact your glucose control. So balancing this all is really, really hard. And to make matters worse, even if you do a great job managing your blood sugar across the lifespan, the condition itself can actually impact tissues across the body. And one of those tissues that we're really interested in is skeletal muscle. Skeletal muscle makes up about 40% of the body, so it's a pretty significant tissue. It's also a huge site of glucose uptake and storage. And perhaps most importantly, muscle is what gives us the ability to be strong and independent across the lifespan. Work from our lab has found that muscle is pretty severely impacted in type 1 diabetes. And typical age-related losses in strength are actually accelerated sometimes up to 10 years, particularly in females. So we're losing strength at a faster rate when diabetes is present. We also found that following muscle injury or damage, individuals with type 1 diabetes actually have a slowed recovery. And this has implications for injury, illness, and bed rest. Now, we're an exercise lab, so we think, these are all factors that exercise might be able to counteract. Exercise promotes strength and recovery. It can improve our mitochondrial quantity and quality. And it may actually help mediate some of these blood glucose fluctuations to give better glucose control. And we're actually not the only ones who think that. In fact, Diabetes Canada actually recommends exercise for individuals with type 1 diabetes. But there are a few critical buts here. The exercise guidelines are the exact same as they are for everyone else in Canada. And perhaps even worse, no one has ever actually tested these guidelines in individuals with type 1 diabetes. So that's what we're doing. We are looking to determine if type 1 diabetes causes any baseline differences in muscle and metabolic health. And we also want to see if the exercise guidelines are able to restore these differences. In order to do this, we're conducting a study that follows the exercise guidelines set out by Diabetes Canada. We have participants both with and without type 1 diabetes adhering to 150 minutes of aerobic activity and 2 strength training sessions per week. They follow these rules for 12 weeks, and we assess them at the start and the end. Now, all of this exercise is done at home in the same way that it would happen in day-to-day real life. So we track activity using Garmin watches so we can see what types of activities you've done, how long you've exercised for, and if you've actually met the targets we've set out for you. We track blood glucose using continuous glucose monitors, which give us minute-to-minute information on blood glucose control. And in our laboratory visits at the start and end of the 12 weeks, we take a whole bunch of measures looking at stuff like strength, aerobic fitness, body composition, and what we're really interested in is actually taking a small piece of muscle so we can get down to the microscopic level and see if there are any molecular or structural differences in the muscle. From these results, we hope to accomplish a few things. We're trying to figure out the best type of exercise for type 1 diabetes. And through this, answer, are the guidelines sufficient? Are they cutting it? We also want to find the areas of greatest loss or gain so that we could better target these with other interventions. And we also want to develop programs that are going to support exercise for individuals with type 1 diabetes across the lifespan. Ultimately, we're looking to improve both the quality and quantity of life for the over 300,000 individuals currently living with type 1 diabetes in Canada. And we hope to do this by keeping them as strong as possible for as long as possible. Thank you.
Great presentation, Dr. McHugh. Thank you for your dedication to such an important and impactful cause. Next, we have Dr. Faizan Salim from McMaster University. Dr. Faizan is a molecular microbiologist with a diagnostics mindset, linking microbial community profiling and targeted detection to real-world outcomes. Skilled in designing and executing workflows for environmental monitoring and clinical screening, with strong attention to microbiome-informed diagnostics for improved public health strategies. Growing up as the eldest child in a joint family with many children, Faizan still finds his only form of entertainment is Japanese anime and manga. So please welcome this anime fan, Dr. Faizan Salim.
Okay, hello everyone. Thank you very much for coming here and attending our talks, listening to us. It's tough, I know. So before I actually begin with what I do or what my research is about, you all would know that a lot of taxpayers' money go into funding our research, right? Millions and millions of dollars. So with great money comes great responsibility, right? So that has been my goal, my motto, to use that money, the taxpayers' money, for their own benefit. What am I providing to the public through my research, right? So today's talk is not actually about me discussing my results. Oh, look, I have this graph or no. No, today's talk is about how through my research I'm actually helping a common man or general public who is actually funding for us. So before further ado, let's begin with a focus on one thing, and that is water. And how many of you actually know what bacteria are? Just raise your hand. Perfect. That makes my life easier, right? You know what is the most common thing between a graduate student and bacteria? They take too long to grow. And by the time they grow up, they may not be as useful. So actually, growing bacteria takes about 24 hours. And more than 90% of the diagnostics being done in clinics, environmental side, or anything that you can think of, right? It's being done through growing bacteria. That means sample collected today would not provide you the answer till tomorrow, right? You may think, oh, just 24 hours. Think about it. You go to the beach, right? You're swimming there, you're enjoying your time, you don't know the water quality yet because the samples were collected today, results would be tomorrow. But by tomorrow you would know yourself because you would be sitting in your toilet whole day with diarrhea. Probably, right? So that's what I'm trying to fix. That's one problem. I want to make the microbial diagnostics faster. So another problem, is you're testing for one bacteria, but you must have heard that there are millions and millions of those, right? What about the others? Are they not there? Are they not important? Are they not pathogens? Let me tell you, there are many of them. But through the traditional diagnostics of growing bacteria, we don't really get additional information, including from viruses, other bacterial pathogens, what are the contamination sources, protists, and so on. That's the second problem I'm trying to fix. Get more information, provide more information, making tests, diagnostics tests robust, comprehensive, and faster. How I'm doing it? The simple answer is DNA. Right? You all know DNA. And specifically, I'm talking about the DNA that is present in the water, which is and the DNA is coming from all the bacteria, viruses, all the organisms that are interacting with that environment. Right? So the first things first, how to make the diagnostics, water diagnostics or clinical diagnostics faster. We do it by targeting the DNA region of the targeted organism instead of growing that bacteria or growing that organism. So instead of getting the results in 24 hours, we can use the DNA amplification technology by get the same results in about 4 hours. Makes it much faster, right? Makes your life easier. And if you want to read more about it, of course, you can read the manuscripts that I have published. Again, I'm not going to discuss any results here. I'm just trying to make your life easier. Second, more target specific, right? Making things error-free, foolproof. When you're testing for something that is a pathogen, you don't want any errors in there, right? So another part of our research, or my research, is basically identifying through our collaborators certain DNA segments, very specific DNA segments that are present only in the targeted bacteria, but in no other organism. Right? That part of the DNA. We use that to develop amplification or DNA targeting strategies that can give you error-free, foolproof diagnostics, and you know that the results that we are getting are actually 100% true. If you want to read more, of course, you can look into the manuscript. The third one, as I said, when we grow bacteria, we're going one at a time. We are not getting the additional information out of it. What about the harmful algal blooms? What about the protists, viruses, and stuff? You must have heard about DNA sequencing, right? We can use the DNA sequencing to develop strategies, and that's what I do as well, to not just target one bacteria at a time, but the entire population, what are there and what they can do. So you get the entire profile of it. You get the entire spectrum instead of just targeting one thing. And again, if you want to read more details, it's the manuscript. Last but not the least, identifying the contamination sources or fecal contamination sources in the context of water. You can keep on testing water forever, but that doesn't get rid of the root causes, right? To get rid of the root causes or for the long-term preservation strategies, we want to identify where that contamination is coming from. So again, using the DNA sequencing technology, we can identify the biological fecal contaminants and develop the preservation mitigation strategies to stop the influx of that contamination into the waters to fix the root cause. And you can read further about it again. And thank you very much for listening to me.
Thank you for such an interesting talk, Dr. Salim. I'm so grateful that we have people like Dr. Salim working on such important issues. Our fourth speaker of the evening is Dr. Jose Patrick from McMaster University. Dr. Patrick is a transdisciplinary researcher. His research and teaching are deeply rooted in community-based anti-colonial praxis and advanced critical social science understanding of systemic injustices and equity issues, particularly as they affect historically marginalized and migrant communities. Through a transdisciplinary lens that bridges political theory, environmental governance, and participatory policy analysis, he conducts community-driven research that interrogates the theoretical interpretations and policy implications of global challenges across the local and comparative contexts. This approach reflects his commitment to methodologies that are collaborative, justice-oriented, and attention to lived realities of vulnerable populations. Something you may not know about this research-driven academic is that Patrick actually owns his own car dealership right here in Hamilton, so you can look him up. He acts and directs stage drama and can also play the bass guitar. So please welcome the multi-talented Dr. Jose Patrick.
Thank you. My name is Jose Patrick, and I will be discussing one of my research, which is deliberative governance and climate geoengineering, community perspective on justice-oriented framework. So before I start, I want to tell you about the biggest bird in the world, which is the African ostrich. It's 9 feet tall and weighs about 340 pounds. One myth about the African ostrich is the fact that when it faces a problem, what it does is it hides its head and then leave the entirety of the body outside. You just wonder. My daughter also does the same. When she doesn't want to talk to people or see people, she closes her eyes and assumes that nobody exists, right? We do the same. I just want to say that climate change is happening, and it's not a myth. It is happening. One of the proposals that have been put out there is what we refer to as geoengineering. It's a climate intervention platform, and the argument is to say that even if we stop greenhouse gas emission, the Earth will continuously get warmer. So for that reason, this proposal comes to play. So you ask yourself, what is climate geoengineering? It's basically the use of large machine technologies to alter the Earth's environment, the Earth's climate. This is what I want you to imagine, this room. If it's hot in this room, what do? We increase the heat, right? If it's, we increase the air conditioning. And if it's cold in this room, we increase the heat. Now, I want you to imagine the same thing if we can do the same thing for the entirety of the world. That is what geoengineering is all about. And in most cases, we tend to want to ignore geoengineering and assume that, no, we should not be doing things like that because of the effects that it will probably come up with. But if we do that, we are practically doing the ostrich approach. And that is where my research comes in, because I believe that the impact of geoengineering, though it's global, the impact is country-specific. The vulnerability is country-specific. The uncertainty, we don't know what will happen if we try this technology, right? And so the uncertainty is high. And then the potential for technocratic lock-in is very high. So for that reason, it is important for us to look at the concept of geoengineering. And why should we do that? We look at it from a justice point of view. First and foremost, we ask ourselves, who benefits from geoengineering? Who is at risk of geoengineering? We also ask ourselves, who is involved in the decision around geoengineering? Who is on the table? Whose voice should we adhere to, or which voice are loudest when it comes to the concept of geoengineering? And what I do is I look at it from a governance perspective, community engagement perspective, and it's from a policy, bottom-up policy approach. And what that implies is that communities meet and they will discuss our perspective and we listen to people's opinion as relating to what is important and what is not important for them when it comes to geoengineering. And the preliminary findings for me so far is the fact that I realized that governments are more reactionary than pro-actionary when it comes to different climate intervention strategy. And there's a need for us to understand what the community is saying, not some rogue scientist or somebody that is excited about science and just want to go ahead and do what, but there has to be a synergy between the science and the community. And for that reason, there's a need for deliberative governance. Thank you very much.
Thank you so much, Dr. Patrick. Your research is truly inspiring and extremely timely. I would like to now introduce Dr. Mona Retta from McMaster University. Dr. Retta is a civil engineer, educator, and researcher with a focus on sustainability through materials, which includes concrete and other cementuous, which is a word I just learned, materials, energy through the energy efficiency of buildings, and society, which includes equity and inclusion through the advancement of accessibility in the built environment in support of people with diverse disabilities. Outside of research, Dr. Retta is always living in a big fat Greek wedding. Coming from a large, close-knit family, she somehow finds the time to stay connected with many, many, many relatives and friends every single day. WhatsApp chats and lively group video calls are simply part of her daily rhythm. She also has a special bond with all of her friends' children in Hamilton. All the kids love Auntie Mona in a way that she is actually their school emergency contact kind of love. So please welcome Dr. Retta to the stage.
Hello, everyone. So, when I studied civil engineering, I always wanted to create an impact on the society. And I was fortunate that my research gave me this opportunity. Let me take you today through my research journey from healing concrete to healing spaces. And to do so, I'm going to introduce my buddy, Mr. Cracky. Hi, Mr. Cracky. So Mr. Cracky was a happy, cheerful concrete structure until cracks starts to propagate into its core. Additionally, Mr. Cracky was designed with inaccessible narrow doorway, confusing layout, and steep stairs. This is when we, civil engineers, had to step in, and everything changed. Civil engineers do not only construct and design. We consider various aspects, from construction material moving forward to the structural design and providing accessible environments for everyone. Talking about construction material, let me zoom in on the problem. As winter approaches, Canada's bridges, structures, and roads all face familiar problem, cracks. These cracks propagate into the concrete core, allowing for liquids, harmful materials, and gases to penetrate through the core, compromising the strength and durability over time. And not only this, the cost of repair is billions of dollars every year. These unavoidable cracks, though, need to be healed or repaired. This allowed researchers, or actually encouraged researchers, to think outside the box. So when your skin is cut, it heals by its own. And inspired by nature, this is how researchers reimagined concrete with a similar ability. And guess what? They're right. Concrete can self-heal. However, since it's man-made, it needs an extra help. And this is what we do at Dr. Chidiak's lab at McMaster University. We provide concrete with an extra help through integrating what is called self-healing capsules within the concrete. These polymeric capsules contain healing agent. When the crack initiates and then propagates within the concrete core, they rupture the capsules, releasing the healing agent to fill the cracks. However, even with the successful or promising approach of self-healing, the concrete has its own properties. Capsules, same thing, and the interface between them, same thing. And all of these properties need to be compatible with each other, which raises many questions. We attempt in our lab to answer these questions by developing numerical models employing fracture mechanics and finite element, and designing experiments. Our goal is to find out what is the optimum design conditions for the capsules to be compatible with concrete. We also look at aspects that allow the capsules to survive the mixing. So what if the capsules ruptured during the mixing conditions and did not do their job later on in filling the cracks? And we try to develop a test in order to test the efficiency of the overall performance of the self-healing system. So our goal is to figure out what are the optimum design conditions in terms of geometrical and mechanical properties of the capsule to stay intact in the concrete mix and only rupture upon cracking to be able to fill the cracks later on. Because if the capsule debonded, they're going to leave voids within the concrete, and also this healing agent will be rendered ineffective. We also look at evaluating the survival rate during mixing conditions, because again, if these capsules fail to survive the mixing conditions, whether due to being stretched and ruptured or being punched by the aggregate within the concrete, this healing agent will be wasted. We're also trying to develop a test, a standardized test, to test the efficiency of the healing system. Okay? And to do so, we're trying to develop the test from a derived test, internationally known as a restrained shrinkage ring. This test allows us to capture the stress development within the concrete as well as the age of cracking. And once we know the age of cracking, we can try to solve the problem as early as possible. Are you still wondering about the title? Well, even in 5-minute talk, I still want to emphasize my role as civil engineer and researcher, which extends beyond healing material to healing spaces. And by saying healing spaces, I mean providing accessible and inclusive environments for everyone. But this is for another talk. To check out our work on accessibility, please scan the barcode. Thank you so much.
Thank you so much, Dr. Retta, for showing us that engineers do not just fix concrete structures, they make them more accessible and sustainable. Our next speaker from this evening is Dr. Nicholas Simard from Toronto Metropolitan University, or TMU. Dr. Simard is a biomedical engineer specializing at the intersection of big data and neuroimaging. After earning his PhD from McMaster, Nicholas joined the LIVELab at TMU to translate complex MRI and CT data into clinically impactful tools. His research focuses on multimodal integration, developing novel machine learning methods to unify these imaging types to identify brain variability and ensure that high-risk patients receive a clearer, more accurate diagnosis. Although French-Canadian by birth, Nick traded in his Maple Leaf status for the sun for a little while, where he spent 2 years island hopping in the Philippines with his wife, where he finished writing his PhD thesis in paradise. Don't we all wish we were there in a Canadian February? Please welcome Dr. Nick Simard.
Medical imaging is a marvel. It is a window that lets us see what lies within without ever picking up a scalpel. With medical imaging, we can see the intricate architecture of the human brain, like in this magnetic resonance image, or MRI. But more importantly, we can see when tragedy strikes, like in this computed tomography, or CT scan, showing a life-altering stroke by the arrow in red. The goal of my research is to use these marvelous windows to not only understand the outcome of a stroke, but also identify who is at risk and how can we prevent future complications. My name is Dr. Nicholas Simard, but you can call me Nick. And I work at the Image Analysis and Medicine Lab at TMU. I started my journey in MRI because it is the gold standard. MRI is incredible at differentiating between tissue-tissue boundaries, those fine edges and borders between different parts of the brain, like in white matter or in gray matter. And using MRI's tissue precision, we're able to find subtle stroke warning signs like intraplaque hemorrhage, or IPH, which manifest as small white spots on an MRI. But IPH, they're unstable collections of plaque, acting like a ticking time bomb. When they go off, a stroke happens. In my most recent research study, I investigated over 300 patients who are historically susceptible to stroke and found a striking IPH pattern. Men over the age of 70 are 5 times more likely to suffer a stroke within a 2-year span if they have a dominance of right-sided IPH. This discovery enables clinicians to intervene and provide life-saving treatments to this high-risk population before tragedy strikes. But, reality check, although it provides a wealth of information, MRI is a marathon. It takes at least 15 minutes just to take a baseline brain scan. On top of that, there's an issue of access. MRIs are expensive. They require massive magnets, specialized hypercooling, and heavy infrastructure. For context, in Canada, we only have 450 MRIs for our 40 million plus population. And in stroke, where every second counts, we don't have time to wait for beautiful pictures. We need answers now. And that is where CT takes the lead. If MRI is a marathon, CT is a sprint. It's accessible, inexpensive, and can capture a comprehensive brain scan in under 1 minute. This makes it essential in fast-paced environments like the emergency room. So think of CT as our first responder in identifying a stroke. But while CT is really good at giving us the big picture, it's not sensitive to detect tissue health. So things like IPH go undetected. So, CT versus MRI. What's the most valuable modality? Well, what if I told you we didn't have to choose? By using multimodal medical imaging, I'm developing a translation software that standardizes both CT and MRI so they speak the same language. With using machine learning, we are able to map CT images directly into the high-detail MRI space, essentially teaching a computer to extract MRI-level knowledge from a CT alone. This is a game changer because now we can take that 1-minute scan, translate it, and identify those previously invisible IPH ticking time bombs. With this translation software, whether you're a young mother in the heart of Toronto or a senior scientist all the way in Nunavut, everyone gets the same gold standard care. And on top of that, this multimodal framework isn't limited to stroke. We can adapt this for diseases like Alzheimer's, Parkinson's, even multiple sclerosis, providing sophisticated research insights to all neuroscience communities. So with my research, in my future, we treat like CT, prevent like MRI, all at once, to ensure that every patient gets the proper care in the nick of time. Thank you.
Thank you so much, Dr. Simard. What a fascinating subject. Looking at our next speaker of the evening, we have Dr. Mallory Terry from McMaster University. Dr. Terry is a oh, sorry, I'm jumping ahead. Nope, I'm good. Mallory Terry, I had to remove one of our scientists, so I'm all over the place now, is a cognitive scientist with the McCall MacBain Postdoctoral Fellow Teaching and Leadership Program. And she's right here in the Department of Psychology, so she lives in this building a lot of the time. Her focus is on attention, perception, and action, investigating how visual information guides action in a world that just won't sit still. Her work bridges laboratory attention research with real-world performance, revealing how perception shapes coordinated action in contexts like things like sports. We're all watching the Olympics right now. This is where she shines. A fun fact about Mallory, she was born on New Year's Eve. So please welcome Dr. Mallory Terry to the stage.
Elite sport often looks like a test of speed and strength. Yet some of the most decisive moments in high-level competition unfold far too quickly to be explained by physical abilities alone. For example, let's check out Connor McDavid's goal at the Four Nations face-off last year. And if you haven't seen this before, pay attention to 97 in red in front of the net. The puck was on his stick for a fraction of a second. Players are closing in all around him, yet somehow he spots an opening and buries the puck in the back of the net. But what if I told you that when Connor was doing this, he was employing the same cognitive processes that you and I use on a daily basis? For example, think about yourself making a left-hand turn at a busy intersection, pedestrians and cars swirling about. Or maybe you're weaving through a crowded shopping center trying to find your friends as they're rushing towards the store that has the sale. So how is it that we can attend to what matters and coordinate action among all of this visual chaos in our world? Well, one hypothesis is that we use what's called fingers of instantiation, and we assign these to key objects in our environment to track their locations and provide us with position references. And so, for example here, Connor might be assigning one of his mind fingers, as I like to call them, to Marner over there, maybe one to the puck, maybe one to that player in front of the net that he might want to pass to, leaving him left with one to pick a spot and bury the puck as he always does. Now, in the laboratory setting, we can model and study these complex visual environments using what's called the multiple object tracking task. And I don't expect you to just take my word for it, so why don't we all try it out? Your job here is to keep track of where all 4 of these spies are hiding as they scramble around on the screen. Good luck. Okay, so what you probably notice is that it is a tricky task, but it's possible. And what we typically find is young adults can track about 4 objects at once under standard conditions. But we only have 2 eyes, so how do we do this? Let's think back to those mind fingers that I mentioned earlier. So according to these mind fingers, we assign them to key objects in our environment. So likely those objects that were hiding the spies, you would have assigned 1 to each of those, and they would stick with them to track their locations. But remember, I talked about the fact that these mind fingers also help us to direct action. And so what I did is I really put these mind fingers to the test, and I designed a series of experiments to really test this out. So people were tracking the spies, and in some trials, I asked them to reach out and touch one of the items that they were tracking. Now, because these items should have the mind fingers assigned to them, they should be able to do this pretty quickly because they have that location reference already. Now, on other trials, they had to reach out and touch one of the items that they weren't tracking. And remember, they shouldn't have a mind finger assigned to this item, so they wouldn't have a location reference. They don't know where it is. So what that would mean is they have to reassign one of the mind fingers to this other item, which would slow them down, and they probably would lose that other spy, perhaps as many of you did. So that's what we would expect. Now let's see what we actually found. Okay, so here on the y-axis we have error rates, and we see that when people are tracking while touching items that they're already tracking, they make pretty few errors. But when we ask them to instead reach out and touch items that they're not tracking, we see the error rates more than double. They go way up. And we see the same trend with the response times. So we see here, in that blue bar there, when participants are touching items that they're already tracking, they're pretty fast to do this. That mind finger seems like it's giving them the location reference. But in the green bar there, when they have to reach out and touch items that they're not tracking, there is a cost associated with this, and they're much slower. It's almost like touching that item is like tracking an additional item. So it really slows them down. And we see that the mind fingers are doing both tracking and providing them with those location references as we might predict. Okay, so what do we make of all this? How can we use this to better our own lives? Well, if you take one thing away from this, I want you to be mindful of how you're using those precious mind fingers. You only have 4 of them. So when you're driving your car, you might be tempted to reach out and change the song or text your friend. But remember, that's going to take 1 mind finger away from your important task of tracking the objects on the road. Or if you're Anthony Stolarz, this means you want to avoid cross-checking players in front of the net. So that's going to take 1 mind finger away from the puck, which is a very important thing to track. Thank you.
Thank you so much, Dr. Terry, and a huge thank you for not using an overabundance of Toronto Maple Leafs references. They could use a little more training on their utilization of mind fingers, I think. Next, I bring you Dr. Ramis Arbi. Dr. Arbi is a postdoctoral scholar in the Faculty of Engineering at McMaster University. During his PhD in engineering physics, he worked on the fabrication and characterization of designer nanoparticles for energy devices. Currently, his research with Nico Hildebrandt in engineering physics looks at developing FRET-based optical sensing applications for biomarkers and environmental pollutants. Outside of the academy, Dr. Arbi rescues old computers and electronic equipment. His greatest rescue to date is a 20-year-old monochromator, I hope I said that correctly, and a 1986 Macintosh Plus, which he brought back to life. So please welcome the Dr. Frankenstein of electronics, Dr. Ramis Arbi.
Hello, everyone. Today, I'm going to be talking to you about detrimental heavy metals and where to find them. So heavy metals are bad. They're bad because they cause developmental issues. They can have reproductive issues. They can cause drastic effects on multiple systems, organ systems. And in fact, different environmental agencies, including Health Canada, have limits on how much of these heavy metals you can have in things like your drinking water. And they range from 1/1000th of a gram per liter to 1,000th of a gram per liter, which is very, very, very small amounts. And you may have heard about exposure to heavy metals through aquatic sources, where small animals are consumed by larger fish, and so on and so forth, till you accumulate these heavy metals till they reach humans. But that's not the only source of these heavy metals. You can get heavy metals in your drinking water, either from a lake, a river, an aquifer. And these are usually sourced from human activities such as mining, landfills, or agriculture, or from natural sources such as erosion. In fact, if you're living in the city of Hamilton, the city has an advisory that you may have lead in your tap water if you're living in an old enough house, or if there's lead plumbing along your service route. Canada by itself has 7 to 9% of the world's accessible fresh water. And respect, they have a multi-barrier approach to protecting these lakes and rivers and aquifers. In fact, if you're living in an urban city, you have free access to testing of your drinking water that is supplied to your house. But there are wells, there is groundwater, and that's how a lot of remote communities get their water. Sparse water treatment and sparse water testing result in underserved communities. And that's Canada with its resources and a lot of water. There are developing countries where this entire impact is compounded, especially so for underserved communities within developing countries. In fact, if you're living in Canada and getting your water through a groundwater supply, you're responsible for your own testing. That brings me to how you test these ions in water. You can use a variety of different techniques. I'm not going to go into the details, but they range from accurate, very accurate, to not very accurate. And in the opposite direction, they range from accessible to least accessible. So you can either know exactly how much you have, but require a lab and trained personnel, or you can know ballpark how much you have, or at least how little you have, and you can do that at home. My research is trying to bridge this gap between accuracy and accessibility, and my champion in this battle are optodes, which use optical sensing, which is basically a mechanism in which you get a conversion of interaction of light and matter into a sort of quantifiable signal. In fact, if any of you are wearing smartwatches, that's exactly how your heart rate and oxygen sensors are measured, so that's what the green flashes are all about. A basic structure of an optode requires 3 parts. There's a sampling medium, sampling interface, which is the part that touches your thing being measured. There is a material exchange medium, which is how that analyte from your sample travels through the transducer, and the transducer is the brains of the operation. It's the thing that changes in response to an analyte. My transducer are these voltage-sensitive dyes, which respond in one of 2 ways. They either change in brightness, or they change in color. While designing this device, there are a few considerations to think about. I want this device to be continuous. I want this to be able to measure things right now, instantaneously, not something that I drank yesterday or I was drinking 5 minutes ago. I need this to be robust. I don't want it to get destroyed just by putting it into water. And I need this to be chemically stable. So I need to be able to put it in different kinds of water. And also, I want it to be specific. If I'm measuring lead, I want to measure lead, not magnesium, not zinc, lead. And so my device looks a bit like this. It's a wand with a little disc at the other end that you can see in pink. And it's wired using optical fibers to a photodetector and a light source. And the pink disc at the other end is just made up of many, many small pixels, each of which are these polycarbonate stable pillars, which are dyed with this polymer, ormocil. And the signal from the dye in the ormocil is measured against the reference dye using the detector, and that's the signal that you're measuring, which is converted into a concentration. In fact, this dye is so porous that you can see a representation in, well, I made that, it's not an image. You can see a representation where gray is where the water would be and the white is where the polymer is. This allows efficient exchange of the analyte between the water and your dye molecules, so a change in pink can be very quickly measured. So my solution to this is using photostable, thermally stable, and chemically stable materials to make a device that has been tested with pH sensing. So changes in hydrogen ions due to acids and bases, which I'm trying to convert into changes in lead concentration because of hydrogen ions produced as a result of that interaction. And the dream is to turn this into a self-contained pen that can be used as a thermometer. Thank you.
So in your schedules, you'll see that Dr. Cameron Murray is actually scheduled to be next. He will not be with us this evening, so we're going to jump right to our final speaker. Our final speaker of the evening is Dr. Melina Esser. Dr. Esser is a postdoctoral researcher in the Kid Lab at McMaster University. She holds a PhD in toxicology from the University of Saskatchewan and earned her master's degree in ecotoxicology in Germany in 2020. Melina's research focuses on how microbial communities, both environmental and host-associated, respond to human activities and how these changes influence ecosystem function, diversity, and antimicrobial resistance. However, it is not all microorganisms in research for this postdoc. Melina has an interesting hobby. She's obsessed with old cameras. Her and Ramis should talk, I think, maybe. Huh? The oldest in her collection is over 70 years old and still going strong. Please welcome Dr. Melina Esser.
All right, hi, welcome everyone. Really excited to be here and present with such an amazing group of presenters. My name is Milena, I'm an ecotoxicologist, so I study how pollutants affect environments. And right now, as part of my postdoctoral research, I'm working on an experiment that might actually be the biggest experiment I'll ever be part of, and that's what this talk is going to be about. But the story really starts here with every one of us. Every time we use disinfectant wipes, fabric softener, or shampoo, we're releasing something into the world called QACs, quaternary ammonium compounds. These compounds are the active ingredients in these products, and we talk hundreds of products. They go down the drain, they enter waterways, and still, we don't really know what happens once they end up there. And that's what we want to find out with this experiment. Now, this is where it gets interesting. So there's a picture of us on one of our research lakes in Northern Ontario, and if you look really closely, you can see a thin white line behind that boat, and that's QACs that we add to that lake in that exact moment, and that's the experiment. Now, some of you might be thinking, wait a minute, you're polluting a lake with QACs? Well, let me explain. So first of all, what are QACs? QACs is a large group of compounds, but to really show you how they work, let's focus on one example, benzalkonium chloride. It's one of the most widely used QACs and also the one that we use in our lake experiment. It has a permanent positive charge at its nitrogen atom, which is really the characteristic of QACs. This positive charge makes it attracted to the negatively charged surface of microbial cells. Once it attaches, it punches holes into the cells, and the cell ultimately dies. And that's how these products clean. Now, there are two major issues with this. First of all, they're non-selective, so they don't just kill the germs, they also affect beneficial bacteria and even other organisms. The second issue is that what we see in our environments is that these compounds don't break down easily. They're basically persistent, which means that they affect these environments long after they enter them. So our research question is simple. What happens to an entire ecosystem if we expose it to QACs? Now, some of you might be thinking, can't you just test it in the lab? And yes, we do, but the lab is missing one very important thing, and that is realism. In a real lake or river, we have thousands of species interacting. We have temperature swings, sediments. It's just way too complex to look at it in the lab. Now, we do have environments where we find QACs. Why aren't we looking at these systems that are already polluted? Well, unfortunately, these systems are also polluted with pesticides, pharmaceuticals, microplastics. So it's basically impossible to isolate the effect of QACs. There would always be the counter-argument, how do you know it's the QACs and nothing else? And that's why we performed this experiment at the ISSD experimental lakes area in Northern Ontario. So this is far away from human activities. And if we see changes there, there's nowhere else to point a finger. And that kind of smoking gun evidence, that's what's changing laws. Now, this experiment is very big. It takes 2 years of exposure, and it includes a lot of different working groups. Some are focused on where QACs go in the system, other focus on fish health, on macroinvertebrates. We try to track everything. It's like a big puzzle and everyone has their individual piece. Now what's my piece of the puzzle? At the Kid Lab, we focus on microbiomes. So these are complex, tightly knitted communities of bacteria that either live in the environment, so you find them in sediments or biofilms, or are associated with organisms, such as fish or insects. And these bacteria are really critical for these species. Without them, they can't survive, and the environment can't function. We use DNA techniques to track who is there, what are they doing, and most importantly, how are they affected by QACs? And remember, QACs are designed to kill microbes. Now, we already have some data from our lab experiments, but let's just say they are concerning. But now we get to see what happens in the real world. And the data we are collecting will help us make informed decisions how to regulate QACs and drive safer alternatives. Because right now, every time you reach for that disinfectant vibe, these compounds are affecting microbial communities in our environments. So the data will help us to understand how exactly do they do that, what happens, which will allow us to make more and better informed decisions on how to clean our homes without compromising our waterways. Thank you.
Thank you so much, Dr. Esser. You've certainly ended our talks on an intriguing, albeit terrifying, note. At this point in the evening, I invite all of our speakers to join me on the stage. I'll give you a moment as you walk up. You can just walk up here. You don't have to go backstage this time. We will now open the floor as well for audience questions. If you have a question for any of our speakers, please raise your hand and a volunteer will assist you with a microphone. I would also ask that you take this time to go online and vote for your favorite talks using the QR code in the corner or the QR code that you can find as well on your schedule. Pardon me. And for the Q&A within the audience, there will be individuals coming to you in the crowd with a microphone so that everybody online can hear you as well. So if you have a question, simply raise your hand and one of our lovely volunteers will come and assist you so we can hear your voice. I will now ask Joe to come out as well to assist with the questions. Thank you, Joe.
Okay, we have a couple volunteers that are going around looking for any questions. Don't be shy. This is your chance to ask our 9 experts in front of us a question that you have. Yes.
It says 1 to 10, but you can only vote to 5.
One moment, please.
Yes. Yes, I'm back. What was the question about voting? Oh, sorry. Just rank. Each postdoc will be listed, and then you can rate them. So don't worry about the ranking. Just give the ratings for each one. You don't have to rank order. So just skip that question. 5 is the highest. 1 is the lowest. Okay? So if you have a favorite, give them 5. Okay? I know, I edited maybe today. All right, so let's go. 5 being the top. High numbers equal high score. 1 being the lowest. Yes. I will allow you to re-vote. 5 is the top score. 1 is the lowest score. Online? They can do the same. They'll hear me talking. So online folks, number 5 is your top score, and 1 is the lowest score. The 1 to 10 was for the rankings. Clear as mud? Beauty. Off to Joe.
All right. Not sure this microphone is working. All right. Who has a question for one of our postdocs? Okay, right there. And who's it for?
Okay, he has. Oh. Sorry, just. Okay, we'll get you the big.
Sorry.
Not getting anything. There? All right.
There we go.
Here's a little bit here.
Hello. Okay. So I'm on. I would like to thank for a beautiful presentation from Dr. McMaster. And my question for you is, what are the alternatives, or like what are the alternative products that we can use to not produce these QCs? Or I'm not sure, I'm sorry. QCs.
Yeah, that's a great question. Unfortunately, right now, it's really almost impossible to not get in contact with these compounds, especially the benzalkonium chloride that I talked about. They spiked a lot in usage during COVID because they're so great in disinfecting. But yeah, the alternative in terms of disinfection would be going more on an ethanol-based or alcohol-based disinfectants. But really for anything else, it's really difficult because they're a large group of compounds and there are a lot of different products. So for you to decide whether or not this product has QCs in them or not is really hard to do. And even for us, when we go out to that lake, it's like we have to check all our products. Do we have any QCs in any of them? But because we have so much cross-contamination because they're everywhere.
Thank you, everyone, for these really amazing pitch talks. You all did really great. You should all win. I have a question for the MRI gentleman. So I was wondering that the CT imagery looked obviously more noisy with less resolution than MRI. And aren't you sort of interpolating a lower parameter space to a higher one? And how can you actually make sure that you're not just amplifying noise by interpolation?
So that is actually a common misconception. CT is actually geometric truth. It actually has the highest spectral resolution because it uses X-rays. And however, it does look blurry, and the reason is there's poor tissue-tissue contrast. So contrast resolution reigns in MRI land, spectral geometric resolution reigns in CT land. And so that's why it's still, very high resolution. It's just the crosstalk between tissues is very different. But by standardizing CT into a similar signal as MRI, then you're able to learn both feature spaces, which have strengths of their own. And if you're able to, again, to standardize them both to their strengths, then you're able to go back and forth between them.
Fantastic, thank you.
Thanks again for the talks. I had another question, kind of piggybacking off the last one for Dr. Nick. So the
I love that. Thank you.
so the on the MRI, we were able to see like these small white dots that were representative of plaques. Do those show up on the CT and kind of get interpolated into the MRI, or how does it work in using the CT scan to find these plaques, or is that not one of the features?
Right, by standardizing the CT image and standardizing the MR image, once you translate them, then on like the translated CT, you're able to identify those plaques a lot more. I will also say those plaques are highlighted for kind of visual appeal. They're a lot hard, like they're very hard for a radiologist to identify. It's more of like a mathematical construct that we're able to kind of untangle once we perform our statistics on the MRI data itself. But that's the beauty of using machine learning, is that our machine learning algorithms are really good at identifying those types of features and making them, go in parallel between CT and MRI. And so that's why we're kind of able to identify these synthetic IPH plaques from the math, from the CT image alone, if that helps answer your question.
Yep, thank you.
Thank you. That's my daughter. Thank you all very much for your talks. They're very interesting. I have a question for Dr. McHugh. During your pre-assessments, did you find any structural or molecular differences when you did the small biopsies on the muscles?
So currently, actually, my little lab assistant in the back is doing a lot of that work right now. Say hi, Ria. So she's looking currently at the samples we have from the study that's ongoing. She's investigating factors like, what is the fiber type? So are they predominantly endurance? Are we looking more power? We're also looking at stuff like capillary density. So how much blood flow is actually getting to the muscle, because that can also be impacted. And we have a lot of samples that are undergoing electron microscopy to actually really zoom in. And we're finding, and this is all very preliminary, some very interesting morphology sort of the mitochondria, and then also glycogen deposits within this tissue. We don't yet know if that's actually anything, but at our sort of like cursory first glance, we're able to get in, like zoomed in pretty hardcore if you can actually see the individual mitochondria. And we're hoping that might actually provide some insight as to why those strength losses might be happening sooner. Why is the muscle taking longer to recover? Because currently we don't really know. We just know that it happens. And so that's kind of what we're trying to use that data for.
Interesting, thank you. One more serious follow-up. Team Edward or Team Jacob?
Oh my God, don't put me on the spot like that.
That's okay. You don't have to choose, don't worry.
No, it's Team Edward. Like, if I said anything else, I
should
have my PhD revoked.
I really enjoyed all the talks today, and I feel like I learned so much. I have a question for Dr. Muna. I was just curious, so the capsules that you're putting in the concrete, let's say they deploy successfully and they repair the crack. Can these buildings like potentially live forever, or do you eventually have to like repair the building? And is there like an expiry date on how well the capsule kind of repairs the crack?
Yeah. So those capsules will be integrated during the mixing process itself. Okay. So we're putting them as a percentage out of the volume. So you still have capsules to repair but of course once they repair once, that's it. But you'll have more capsules to repair the cracks over the time. In terms of expiry dates, I would say like it's around I'm not gonna say something outside the scope of my research, but based on what I read in terms of the expiry dates for the capsules and so on, since they're polymeric, they can stay up to 50 years.
Thank you.
My next question is directed towards Dr. Arby. Hi, Ramis. So your vision is to have your FRET nano opto measuring system and a thermometer type of device. And so in the final sketch I saw, you have this beaker with the fish, the spinny bit in there. And so do you require the spinny bit, and how do you turn the spinny bit into a thermometer device? So how do you take that apparatus and make it small, including the mechanics? What's your vision?
So the spinny bit isn't actually part of the sensing mechanism. It's just there because when I add lead on the side, it just helps it spread faster. So in the case of, let's say, a river, you'd assume that it's already homogenized. So that's not actually part of the thermometer. It's just there for aesthetics.
Okay, so you just have another source, and then you have your fancy nano thermometer, and you just poke it in the liquid, and you're done.
Yeah, it's basically just passively flow-based. So whatever diffusion you're getting is just from the interaction of the water and the polymer. The thermometer is just there to disperse whatever I add into the beaker.
Thank you. That's serious sci-fi stuff.
Thank you. Thank you for all the great presentations. I want to follow up on Mona. I can't help. I've been living in Canada only for 3 years to make sarcastic comments about Canada, but seeing the building sites here, when you need to put more capsules than concrete in your mixture to fix all those houses? You don't have to answer.
Hi, those were all great presentations. I'm so sorry I forgot your name, but the one that showed the Connor McDavid highlight. So I was thinking when you showed that the things like NHL and NASCAR, it's moving a lot faster than pointing to little guys on a screen. So do you think that athletes have enhanced their ability to switch between their mental fingers, mind fingers, or do they have more of them through training? Like, how are they able to do that so effectively?
Yeah, that's a really great question, and I think those are the kind of things that kind of keep me up thinking at night a little bit, because it is true. Like, are they just born with these enhanced cognitive abilities, or by years of working in their craft, they develop them, and it's sort of like training those cognitive abilities. So it seems like the answer could be a little bit of both. I know I'm not picking either side. The evidence is kind of still mixed, but certainly like in other labs, they've studied some elite athletes in the NHL and the EPL, and they find that they have elite tracking abilities compared to like non-athletes. So there does seem to be some there's some advantages that they have there, but then again, they have played for years and years to make it to the NHL or to make it to the EPL. So it's hard to say what's driving that. So it's certainly a great question, and hopefully I'll be able to tease that apart more as I continue my postdoc research.
Thank you.
Maybe I could just ask a follow-up question there. So you said we should really think about how we're investing our fingers of attention, and you gave the analogy of if you're driving a car, are you changing the channel, paying attention to a call? So a question from a parent perspective, what happens when you have teenagers that are constantly on TikTok and they're constantly using part of their attention? So it's like this chronic thing. I feel like there's no rest. Do you think there's an impact of that on their overall ability to pay attention?
Yeah, that's also a good question. I mean, in some ways, you might think like they're becoming like an automatic kind of task. So it's potentially like something that they can do and have resources to do other things, but likely it is definitely causing them to split their attention. So if they're trying to say your kids are trying to talk to you while they're playing on their phone, inevitably that's taking away from their resources that they have to listen to you, as you maybe have noticed, I guess. But so yeah, I'd say it's forcing them to split their attention, and it definitely means you can give less attention to the things that are important, and that's you and not the phone. So.
Yeah, I live with 3 teenage case studies as we speak. Do we have any other questions? Okay, one thing that some of our audience members might not fully appreciate is that at a university, people know about professors, they know about undergrads and maybe even grad students, but what is life like as a postdoc? Is there someone that could give some insight to our audience of what it's like being a postdoc? Because you're not quite a professor, you're not a grad student anymore, so what are you?
I'm going to deal with this one, yeah? Okay, I'm not going to complain much, right? One pro is that you're going to get a bit more amount than you were getting paid during your PhD. And Joe asked a question like, at what stage do you see yourself, right? So think of it as like there are two islands, right? Since islands are a lot in talk right now, but so there are two islands. One is PhD, and another one is professor. And you are in a boat that is in between those islands. And you're trying to figure out, you can't go back. You can only see ahead to the island that is called professorship. So if you that's what our focus is on. That's what our research is about. We keep on doing what we used to do, but we try to improve each and every single day, and that's what I have seen with every one of these individuals. And 7 of them actually are with me in the McCall MacBain program. So it's when you become a postdoc, it's not just about self-learning. It's also about helping others around you, graduate students, undergrads, your fellow postdocs, to improve, to become a better version of yourself every single day. So, thank you.
Thank you so much. So postdocs really are, they're the engine that drives innovations at universities. And so we're thankful for all of you, for all of the amazing research and everything that you guys do at the universities. Thank you very much. I am now going to pass you on to Katie, who has our results.
Thank you very much, Joe. At this point in the evening, we're going to go through all of our awards, which is very exciting. I've been back there tallying. We had around 200 votes for the popular vote, and I've also tallied our judges' scores as well. So moving forward, and before I announce the winners, I know you have been standing in the hot spot for quite some time, folks. I do apologize. I just want to say you're conducting some amazing work that will one day change our world. Thank you for everything that you do, whether it be understanding attention or organisms in lakes, establishing the importance of community, or investigating diagnostic technology, connecting how our behaviors impact the earth, from global warming to chemicals in our lakes. Postdoctoral researchers drive our understanding of ourselves as well as the world. As a thank you, each finalist this evening will receive an award created by local artist Paul Rodrigue from Dundas, Ontario. I now invite Paul, who is in our audience, to join me on stage to hand out our 2 top prizes. There he is. Thank you, Paul. These glass sculptures that you will see in a moment were created for tonight with the theme of knowledge. Each takes the form of a glass flame or circle encasing the iconic McMaster colors. I find it fitting that the awards for this evening were crafted in glass. Glass is a combination of millions of grains of sand that are fused and transformed by intense heat into something new, much like the hours of dedicated research performed by this evening's speakers that culminate in the creation of impactful knowledge and innovation. Thank you to our early career researchers for creating the intense heat that is required to transform our understanding of the world. All right, first, I bring you the People's Choice as voted by you this evening. The popular vote for the 2026 5MRT goes to Ramis Arbi. Congratulations, Dr. Arbi. Now, the moment you've all been waiting for, your 2026 5MRT winner, who will be the recipient of the top prize of $1,000. The winner is Dr. Nicholas Simard. Congratulations, Nicholas. Thank you to everyone who made this evening possible, to the McCall MacBain Foundation for believing in researchers and leaders of tomorrow, to the McMaster Office of Alumni Engagement, to our amazing researchers, and to all of you for joining us this evening. We hope that everyone has a safe drive home. Thank you. anybody wants to stay back for pictures, please do. We'll have our researchers on stage for just a few moments if you wanted to snap a pic. Oh, it's off. If there's any food, please eat it all. Take the food, take it home, eat tomorrow.